Hi there, so my name's Chris Collison, and we're going to continue today to think about the harmonic oscillator, and in particular today we're going to think about the eigenfunctions, the solution to the Schrodinger equation that we built up over the last lecture or so. Obviously we developed a classical description of the harmonic oscillator, we substituted in the operators and built the Schrodinger equation. In the previous lecture as well, I've talked about the eigenvalues. We've explored the Heisenberg uncertainty principle implications. We talked about selection rules and introduced infrared spectroscopy, and we talked about overtones and how if we need to start to move towards a Morse potential, we have to do some work with the Taylor series expansion in order to develop the potential energy and kind of complicate the Schrodinger equation. But at this point, we've never really talked about what those eigenfunctions are and what the solutions are. So in this particular segment, we'll talk more about those specific solutions. And so we'll start with that. So in this section, this is section 5.8. We're going to think about the solutions to that Schrodinger equation. Here is the Schrodinger equation that we're solving. And it turns out, again, that the solutions themselves and working through those solutions is outside the scope of the class. But what we can do is we can later, my suggestion to you is to plug the solutions into this differential equation and prove to yourself that those solutions are indeed solutions. And that's the beauty of when we're provided with an eigenfunction, we can plug it back in and just check that it works. We don't have to go through all the hard work to actually develop the solution or solve the equation from the get-go. But I'm going to say plug the solutions into the Schrodinger equation and test it. Okay, so without further ado, here is the solution, the generalized solution. And we'll write it as follows. We have psi sub v, that's a function of x. And we can write that in our bracket notation. And the general solution is capital N sub v. What do we think that is, that N sub v? I'll tell you in a second. Capital H sub v. And capital H is a function, and it is a function of a term alpha to the half multiplied by x. And the last part of the solution is this exponential term e to the minus alpha x squared over 2. So a couple of points. What is alpha? So first of all, we're going to say what is alpha. Alpha is simply the force constant multiplied by the reduced mass mu over h bar squared, all raised to the half. What is this n sub v term in here? So n sub v, yes, you guessed it, is the normalization constant. And I'm going to provide that here for you. The generalized normalization constant is 1 over 2 raised to the v, raised to the vibrational quantum number, multiplied by v factorial. And that is all raised to the half. And then second part of the constant, we've got our alpha that shows up again, alpha over pi to the quarter. So that was the normalization constant. What is going on with this function h sub v? So h sub v, so these are what we call Hermite polynomials. So we're going to say h sub v, and they're a function of alpha to the half x. It's just convenient to write a function alpha to the half x. We're going to replace that with a little squiggle in a minute, which is going to be our variable. Again, we're going to shorthand notate it. But h sub v, these are Hermite polynomials. And so I mentioned we're going to do another simplification here. We're going to let this little squiggle in here be equal to alpha half x. That little squiggle. Okay, surely there's got to be enough letters in the alphabet for us to be able to draw on something other than a squiggle, but I guess squiggle is what we're going to use here. Nonetheless, Hermite polynomials, it turns out that the form of the Schrodinger equation that we're solving here, that equation was solved many years before quantum mechanics came along, and so the mathematics could simply be borrowed from the pioneers of math, and so those solutions were sort of pumped directly into quantum mechanics. And so we're going to follow the same kind of pathway here, and we're going to say, again, because these solutions are outside the scope of the class, we're not going to spend too much time thinking about how those polynomials were developed, but I will describe for you what those Hermite polynomials are, and I'm going to put those into the next slide, and we'll come back to these. I'm going to look at some of these functions again shortly. So let's write them down one at a time. So the first one ends up being quite straightforward. I'm going to write them in terms of this little squiggle in here. So there's our function, and remember that squiggle is equal to alpha to the half x. So the Hermite polynomial h sub naught here, h sub 0, is simply equal to 1. We're going to have h sub 1 in here, and that is equal to 2 times squiggle. H sub 2 is equal to 4. I think this is actually called xi in Greek. So maybe we'll call it xi for now. It sounds a little bit more formal. And h sub 3 in here is 8. And there's a little pattern that starts to show up here. 8 xi cubed minus 12 xi. H sub 4 is equal to 16 xi 4 minus 48 xi squared plus 12. And finally we'll go to h5. So these are the Hermite polynomials. 32 xi to the 5th minus 160 xi cubed plus 120 xi. So these are the Hermite polynomials. Putting this all together, we can perhaps write down what the solution is. So if we come back a page in here, we recognize, yes, we've got this normalization constant in here. We've now got our Hermite polynomial, and we're going to find that this last portion of the solution is always the same, this exponent. Let's plug them together and make a note of psi naught now of x. Okay, again, we can use our bracket notation in here. That comes out to be, here's our normalization constant in here, alpha over pi raised to the quarter. Remember, in this particular case, the Hermite polynomial is simply 1, so it's a very simple expression. So e to the minus alpha x squared over 2. Starts to get a little bit more complicated when our quantum number is equal to 1. How would we write that in our bracket notation? We've got a 1 just inside our ket. And this ends up being, so we kind of have to do a little bit of work in here. So we end up first with 1 over 2 to the half. So our normalization constant, and then we've got an alpha over a pi, and that's raised to the quarter. And then we've got our 2 xi in here, so I'm going to multiply by what's xi? Remember, it's 2 times alpha to the half x, and then e to the minus alpha x squared over 2. Let's kind of pull that all together, and what we end up getting there, let's put this in brackets, is 4 alpha cubed over pi, that's raised to the quarter, and x e to the minus alpha x over 2. So what we're going to find is that as v goes up, by the way, the order of x goes up in our solutions. So the order of x here is x to the 0. We've got an x to the 1 in here. We'd find that xi2 as a function of x would also have an x squared in it, and so on and so forth. So that's a trend that we're going to start to observe with these Hermite polynomials. So let's look at psi of x, and how would we write that? Again, in the bracket notation. So let's write this down. It's alpha over 4 pi. That's all raised to the quarter. There's our constant. Then we've got a 2 alpha x squared term minus 1. So there's our x squared term, and then the exponent. And we're just really at this point just starting to recognize the functions and breaking it down. So psi3, again, we're getting used to this bracket notation. What do we expect for psi3? We're going to have a constant in here, alpha to the 3rd over 9 pi, again raised to the quarter. And now we're going to have a 2 alpha x cubed term minus 3x multiplied by e to the minus alpha x squared over 2. So now let's take a look. Here's our first 4 solutions in here. Let's actually take a look at what these look like in a drawing. Let's look at them visually. So before we start to look at these curves, let's actually recognize again we have this exponential decay, right? So moving from x equals 0 outwards, we're going to see an exponential decay in here. But as the quantum number increases, we're going to start to see this this x term in here is going to increase, and it's gradually as x increases. We're going to force the the envelope function. We're going to start to force a peak to exist further and further to the right hand side. And what we'll start to see happen, by the way, is when v becomes very large, we start to approach what we might expect from a classical description of balls on springs, but we'll come to that shortly. So here are those curves, and so what we can recognize at the beginning here is we've just got an exponential decay away from the origin. Remember, x is equal to 0 at this point, and that would be where L is equal to L0. There's our equilibrium position that goes up actually through the middle of these curves. There's no nodes when the wave function is associated with vibrational quantum number 0. We're going to notice there's one node in here when the vibrational quantum number is equal to 1, and we've got 2 nodes in here when the vibrational quantum number equals 2. So these are a couple of things that we can start to see immediately when we start looking at these curves. On the left hand side over here, so these curves are just the wave functions themselves, and this is simply a drawing of those functions. Of course, when we square those wave functions, then we end up getting the probability distribution, and that's the probability distribution is shown on this right hand set of curves in here. So what else do we have in here? We've got the eigenvalues. So remember, the 0 point energy is half h nu, and then we step up in steps of h nu. So we go to 3 halves h nu, 5 halves h nu, 7 halves h nu, and that's for the wave function psi sub 3. We're also going to talk shortly about other properties of the wave function. What we'll see, for example, with psi2, there's some symmetry around the x equals 1 position in here. There's a mirror symmetry, in fact, around the y-axis, and we'll go on to think about that more in a second. Another important thing to remember about all of these functions, of course, is that they are orthonormal. So they're orthogonal. That means that if you integrate psi 0 multiplied by psi 1, we're going to find that overall space, the result ends up being 0. And of course, they can be normalized. And so we see that when the square of the wave function is integrated over all space, we also end up with 1, and so therefore, of course, we have this normalization constant. So that's typical, of course, for all wave functions. What we're now going to do is move into section 5.9 of the textbook. So this particular section is titled Hermite Polynomials are either even or odd functions. And so the question first is what does this mean? So let me just define an even function for a second. So an even function is some function f of x, and that even function f of x is going to be identical. It's equal to you get the same values when you plug in minus x values in there. So if I've got a function, some y value of when I plug x equals 4 in there, and I get some y value that's 16, then if I plug in minus 4 into that same function, then I also get 16. So odd functions are slightly different, and they're defined as follows. So I get minus the function when I change the sign on the value of x I plug in here. So I think this is best explained with some examples. So let's look at a couple of examples. First of all, let's look at a sine function, for example. So here's our sine wave. And really what we have to do is go back to the other side, so into the minus x direction, and we recognize that the sine function is an odd function. Okay, so if we take pi over 2, for example, so here's pi over 2, and the sine of pi over 2 is plus 1. So if I go back to minus pi over 2, I find out that when I plug minus pi over 2 in here, so minus pi over 2, what I get here is a minus 1 in here. So that minus 1 is equal but opposite in sign to the value with plus pi over 2. So we would say that a sine function is an odd function. At the same time, we might say, and these are some of the examples in the chapter, so we have example A, and the function x sine x is provided. By the way, the simple function of y is equal to x is an odd function as well. Okay, here's our function of y equals x. Here's our y-axis, and here's our x-axis here. When I multiply these two together, right, I'm going to get some function that looks something like shown down here. So think about what this looks like. So I'm going to get something that looks like something like this. So now what we see here, this is actually an even function, okay? And I can demonstrate that mathematically in a second, but with the even function, you're going to see this mirror symmetry. So you'll see the mirror symmetry really around this y-axis here. And so this is the sort of hallmark of an even function. So we can look at it graphically, but often the functions aren't going to be so easy to plot. So what we might do in here, how would we determine this? So we're going to say, well, yeah, we've got our x sine x function in here. And then what happens is we're going to try the test, right? So we're going to try to plug in a minus x for every value. I'm going to ask the question mark here. If I plug in minus x for every value of x, what do I get? So I get minus x in here multiplied by the sine of minus x. And so what this also ends up being, so the minus x stays in here, but the sine of minus x, as I've already shown you, it's an odd function. So sine function is an odd function, so that will end up becoming minus so that we can bring that minus to the left hand side, minus sine x in here. So then of course the minuses cancel, so I end up with plus x sine x, and lo and behold we find that the f of x up here was indeed equal to the f of minus x down here. So we would say that this function x sine x is indeed an even function. And so you're asking, well, why is this important? And I'm going to show you shortly how this ends up being really valuable. It saves us a ton of time. Rather than spend a lot of time doing our tricky integrals, we can recognize some true and valuable shortcuts when we recognize functions as even or odd. Let's have another look at a couple more examples. So the examples in the textbook, we've got e to the minus x squared cosine x. We're also going to notice a pattern, by the way. So cosine x is an even function. And the question is, what is e to the minus x squared? Well, we'll do the first, that question first of all. What happens when we plug in minus x for x? So we're going to end up with e to the minus, and we're plugging minus x in here. Remember, that's minus x squared. So I think you can already know what the answer is. So that's multiplied now by cosine of minus x. And so that ends up being, well, when we put the minus x in here, we square that, we're going to get x squared. So we end up with e to the minus x squared. Cosine of minus x is simply equal to cosine of x, because cosine actually is an even function. Okay, so it's symmetric about that y-axis. So we've got an even function here. So an even times an even function, it turns out, is also an even function. So again, any way we look at this, f of x on the left was equal, here was our test, that was equal to f of minus x on the right hand side. So let's just go back a second. Notice what we had here. We actually had two odd functions in this particular example. So we had an odd function for the x, so this was an odd function, and sine x was also an odd function. So it turns out if we multiply an odd function by an odd function, we get an even function. If we multiply an even function by an even function, we get an even function. That will come out to be very important to us when we think about normalized wave functions. Let's look at another example here. And the example C in the textbook is x squared sine x. And well, now we'll plug some values in here. We're going to ask the same question, what happens when we plug minus x in here? So when we replace the x with a minus x, so we get minus x squared sine minus x. So we recognize that this ends up being equal to, well, x squared. So this, the x squared piece, that's an even function. And we also recognize already that sine x is an odd function. So it turns out, by the way, that an even function by an odd function is going to give you an odd function. Let's prove that. So again, we're going to have x squared in here multiplied by minus sine x, which is equal to minus x squared sine x. So then, therefore, we've passed our test for an odd function, right? So for an odd function, f of x is equal to minus f of minus x. So it turns out that this is indeed, this whole thing here is odd. And the key one of the key takeaways here is that even function multiplied by odd function is equal to an odd function. And last but not least, the final example given, we've got an e to the ix, and we ask the question, is that equal to e to the I minus x? Question mark. And what we need to do here is use Euler's principle, so we convert that into cosine x plus I sine x. And of course that is equal to, when we plug the minus x is in there, so we're going to plug a minus x in for this x and a minus x in for this x. We get cosine minus x plus I sine minus x, and we end up with cosine x, because cosine minus x is equal to cosine x, and then the minus in here, so sine minus x becomes minus sine x, so we get minus I sine x, and that ends up being equal to e to the minus ix. The key here is that really e to the ix being equal to e, when we replace x with minus x, we end up getting e to the minus ix. So that it turns out that this is neither, if you go back to looking at our definitions, this is neither an odd function nor an even function. So some functions are neither odd nor even. We're going to focus on so these are completely unequal, all right? So this is completely unequal to this, so we can't categorize it either as an odd or an even function. So now that we understand what even and odd functions are, we can actually go back and look at our Hermite polynomials, and we can say, okay, what are they? Are they even or odd? So if we look at this first, this h1 function in here, we've got the 2 times the xi in here. So this ends up being an odd function. So it's just like the y equals x function. We've got a xi term in here. So h as a function of xi ends up being an odd function. Because of the square term, the xi squared term in here, we're going to have h sub 2 is an even function. H sub 3, again, because of the xi cubed and the xi function. So test these out for yourself. This is an odd function. So you're going to see a pattern here. We go odd, even, odd, even, odd. And so basically, if v is odd, if the quantum number v is odd, then the function is odd. And you're still all saying, well, why is this relevant? How is this valuable to us? So let's have a look. Because I put it to you that knowing whether a function is odd or even is going to save us a significant amount of time. So the first thing I'm going to tell you is if we have an even function, so let's take some function similar to the one that I showed you earlier. Let's have a look at this function in here, and we're going to have a look something like this. So here's this is our x sine x function that I showed you earlier. Let's think about the integral of that over some range from a to minus a. So here's our range. So we're going to put our limits in here in the integral. And let's think about this x sine x. What we can recognize here is that if we sum this all up, we certainly aren't going to cancel anything out. We don't cancel anything out in here. So we're going to basically say that that integral is not equal to 0 automatically. A counter argument, let's look at, for example, x cosine x. So this was an even function at the top, but let's look at an odd function down below. X cosine x is an odd function. What does that look like? It looks something like this. And here's the midpoint. So in a way, actually, we've got some rotational symmetry, right? If we rotate this curve, we're going to see some rotational symmetry. But let's take these limits here again as being minus a on the left here and plus a on the right here. If we start summing up over these values, because of the symmetry that we see, so this region here is going to cancel out this shaded area here, and this negative shaded area here is going to cancel out with this shaded area in here. So it turns out here's the key point in here. So if we integrate over two symmetric points about the y-axis, equal distance apart from the y-axis, and here's our odd function in here, d sub x or dx, this ends up being equal to 0. So this is our odd function here, and we integrate that again from minus to plus infinity, would get a 0 in here. So the areas on each side of the y-axis cancel. Let's go back to thinking of our wave functions. I mentioned earlier that those Hermite polynomials are odd functions, and then we have an e to the minus x squared term, which is an even function. So when v, the quantum number, is odd, we're going to get an odd wave function, and when it is when v is an even number, we're going to get an even wave function. So how do I write that down? Psi odd in here of x. Well, when v is odd, we're going to get an odd function. When v is even of x, we get an even wave function. As I've mentioned, odd times odd is equal to even, and even times odd is equal to odd. And if we integrate over an odd function, that ends up being equal to 0. So this automatically actually demonstrates that there's orthogonality. Certainly with when we have an odd function, v equals 1 multiplied by v equals 2. We're going to have an odd multiplied by an even, and then we integrate that over all space. We end up demonstrating our orthogonality. So we can almost do it qualitatively without actually going through and doing the integration. How else can this be used? Well, let's suppose we were tasked to calculate the average value of x for a harmonic oscillator. So let's think about first setting that problem up. So we look over all space, we run from infinity to minus infinity, and now we take our wave function with our quantum number v, and we set this up. And remember, we place, in order to find the average value of x, we put the operator for x in between the two wave functions. So we actually operate on the wave function. Remember, in this particular case, we're dealing with real numbers, so there is no complex number associated with the harmonic oscillator. So it kind of gets a little simpler here, but we've just been talking about odd and even functions, and so we know that, for example, if the v is the same in this particular integral, so even if it was odd, right, we've got an odd function, and we've got an even function, and we've got another odd function in here. So odd multiplied by odd would give us an even function. And then, of course, we know that our x in here is already an odd function. So independent of whether v was an even number or an odd number, the wave function squared would be an even function, but an even function resulting from the multiplier of, or the product of these two functions, that would automatically be an even, but now multiplied by an odd function. Our rules tell us that this total integral would be an odd function. And what do we know? When we look at the integrals of odd functions, we know that they must be equal to 0. So automatically, this qualitative view on whether functions are even or odd, it tells us, in fact, that the average position of that harmonic oscillator as it's moving backwards and forwards is equal to the average position is equal to is x equals 0. That means L is equal to L naught. So that's one of the things that save us a lot of time thinking about these odd and even values. We can do the same thing, by the way, with if we were asked to find the average value of the momentum. Okay, so another interesting thing here that I want to draw your attention to is that, in fact, before we go there, the first derivative of an odd function is always going to give you an even function, and the first derivative of an even function is going to give you an odd function. So how is this useful? So again, what we're going to do is we're asking ourselves, what's the average value of the momentum for our harmonic oscillator? And again, we'll choose our limits to be infinity and minus infinity. We're going to plug wave functions in here. We don't even need to know what the form of those wave functions is, as long as we know it's odd, right? And an odd wave function multiplied by an odd wave function is even. So, and then we've got, well, in this case, we've got something a little trickier, because we're going to have our operator for momentum, linear momentum, which is I h bar d by dx in here. And so that d by dx is actually going to operate on our wave function. So let's assume it's an even wave function. Let's suppose that v is even. That means the wave function in each case is even. But now when we operate on that second wave function, so when we operate on here with our derivative d by dx, what we're going to end up with, so this is going to give us an even function multiplied by the derivative of an even function is going to be an odd function. We take the integral of that, and again we find with respect to x that ends up being equal to 0. So again here, without having to go through the formal integration, we have found that the average momentum of our harmonic oscillator is 0. That makes sense to us because the oscillator is moving first in one direction, changes direction, then moves into the other direction. So there's the beauty of an even and odd functions. Section 5.10 is basically saying there are many useful relations among Hermite polynomials. It's basically saying, you know what, there's some cool tricks. And there's one cool trick I want to get to where we're actually talking about the selection rules. And how do we get there? There's kind of three steps. The first one, we're going to kind of piggyback off what I talked about in the previous slide. And let's suppose that we want to know the average value for x squared. And so how would we calculate that? Now, let's work with, in this particular example, let's just start with the psi naught wave function in this case. Let's pick the easiest wave function. How would we do that? So basically what we're going to do is we're pulling out well, let's actually remember what that wave function is. It's a function of x, and that's equal to, it's alpha over pi to the fourth, and we've got this e to the minus alpha x squared over 2 in here. Okay, so when we multiply that together, okay, so we've got our 1/2 term in here, because we've got the alpha over pi to the fourth squared, so that becomes alpha over pi to the half, and we're going to find the average over all space. We're going to put the dx in here first of all. We've got the x squared, Okay, so we've got that x squared has to come in here. And then really we've got the e to the minus alpha x squared over 2. So e to the minus alpha x squared over 2 squared becomes e to the minus alpha x squared. Okay, so what's happening in here, right, is we've got psi of naught times x squared times psi of naught dx. Okay, so that's what this is. That's what this expression is. What else can we say? So we know our xi term is equal to alpha to the half times x. We can also say d xi by dx is equal to alpha to the half, and therefore dx is equal to 1 over alpha to the half d xi. Okay, so now what we're going to do is we're going to replace the dx. We're going to substitute in here for the dx. We can also say that basically as x goes to infinity, well, since xi is equal to alpha to the half x, well, basically we say that xi also goes to infinity. And so we're going to replace our limits with, we can replace x equals infinity with xi equals infinity. So we're going to basically write down this integral in terms of xi. So let's do that down here. So here's our x squared. This is the average that we want. We're going to replace everything in here. So we've got an alpha to the half. We're also recognizing that when we replace the dx with d xi, we're going to have a 1 over alpha to the half. So that also ends up, not only do we have alpha to the half multiplied by pi to the half, that's from this piece in here, we've also got another alpha to the half term that comes from this substitution. Okay, so that goes into there. Of course, what we'll find out later is that those terms will cancel each other. I guess we're changing color now. So this is xi is equal to infinity, and xi equals minus infinity. We've replaced the dx now with the d xi. What else? Well, I missed something out earlier. That was an x squared in here. So the x squared, by the way, what is x squared? X squared is equal to xi squared over alpha. So we can replace our x squared with our xi squared, and that's also going to be over alpha. Okay, so there's that piece in here. And then we've got the function in here, e to the minus, we'll replace x squared with xi squared over alpha. Then we're replacing this x squared with the xi squared over alpha, and of course when we do that, these alpha terms will cancel. So that would end up giving us e to the minus xi squared in here. So what does this end up becoming? So we end up getting, of course, for an even function, right? So an even function, let's think about this for a second, the x squared, an even function. Here's a little trick that we can do with this Hermite polynomial. So of an even function, right, it's symmetric about both sides. So we can basically say, well, let's actually go from 0 all the way to infinity, and that ends up being equal, or let's say the integral over the whole curve is equal to the integral from 0 to infinity. So in other words, we look at the total area under this curve, and it ends up being equal to twice the green shaded area in here, right? So with that in mind, what we're going to do now is multiply this whole piece in here. We're going to multiply by 2. So 2 over alpha. So we're going to pull the alpha out. Okay, so that's coming out here. So 2 over alpha pi to the half. And because of that, we're going to change the limits to infinity at the top and 0 in here, d xi squared e to the minus xi squared. And that, how do we calculate that value? Let's get rid of my little sketch. Okay, so it turns out that a standard, right, so we can look this up on the front cover of our textbooks. We'll work with a slightly different color in here, so this is starting to get a bit of a mess, but here's our standard, the integral over infinity to 0 in here, x raised to the power of 2n e to the minus ax squared dx is equal to 1 times 3 times 5 all the way up to 2n minus 1. In the denominator, we've got a 2 raised to the n plus 1 multiplied by a raised to the n. And the last piece of this is a pi over a to the half. Okay, so in our particular case over here, okay, so we've got an x to the 2n. So in fact, let's consider the xi as being our x. So xi is equal to x for the purposes of allowing us to bring this standard integral into play. So we've got a xi squared. So we're going to say that n is equal to 1, right? So x squared, x2n. So we're going to say in our particular case, n equals 1. And we've got a minus, just a minus xi squared. So we're also going to say that a is equal to 1. So when we plug these values in, we go up to in the numerator in here. So the numerator ends up being, well, 2n minus 1. So n is 1. 2 times 1 is 2. Minus 1 is 1. So we're going to have this on the top in here. So we end up, by the way, we've still got our 2 over alpha pi to the half. But the standard integral is going to give us a value that is, in the numerator, we've got a 1 over, so n is equal to 1, so 2 raised to the 1 plus 1 is 2 squared, so that's 4, multiplied by a to the 1. Well, a is 1, n is 1, so that ends up just being a 1. This ends up being 1 in our particular case. So we end up with 1 over 4 multiplied by pi over 1 to the half. And when we calculate all these, when we just cancel we cancel the pi to the half, okay, and we cancel 2 with the 4. So we end up simply getting an answer that is 1 over 2 alpha. That's our final answer. So that was pretty easy. What was the point of that? I'm showing to you, oh, you know what? Actually, psi naught was the easiest wave function that we could work with, and that was kind of a fairly tedious integral. So it's easy, but in general, we still have to evaluate all this. How does working with Hermite polynomials help us? So supposing we wanted to make that same calculation, but we wanted to do this generally for any particular wave function for any particular quantum number, right? So again, remembering our bracket notation, how could we demonstrate what we just demonstrated? How could we calculate this? Let's just remember what psi v is. Okay, so there's a v in here, and that's equal to n sub v h sub v, and that's a function, by the way, of alpha to the half x e to the minus alpha x squared over 2. So there's our function. So let's put this all together, right? So what do we get? So our average value is equal to, we can bring the normalization constants outside the integral. And then we are left with hv function again. It's all laborious, right? There's our x squared value in here, and then here's our hv term all over again. And that's the full integral. Okay, so now what we do is we start to replace again with the with xi in here. So first of all, we're going to write this out a lot in longhand. Okay, and this really proves a point how tedious this can be. So we're going to replace the alpha half x. That's easy, first of all. And keep the x squared in there, and then we got this hv e to the minus alpha x squared over 2 dx. Again, we can actually make this easier on ourselves. So another simplification, we're just going to multiply these two functions together. So this function multiplied by this function. And what happens is, when we do that, of course, is we can remove that divided by 2, and then we're going to cancel this term completely. So we've multiplied those together. So rather than rewrite it for you, this is what we end up with. Another thing I'm going to point out here is that we remember that xi squared is equal to alpha x squared, and also the dxi by dx is equal to alpha to the half. So this expression now becomes, is our normalization constant, as our limits. So now we've got e to the minus, we're going to replace the e to the alpha x squared. All right, that becomes e to the xi squared. Okay, so now we've got h v xi, and the xi squared, of course, or x squared is equal to xi squared over alpha multiplied by hv. This is very similar to something that we saw in the previous slide. So we're just gradually simplifying this. What we'll next do, of course, let's bring the alpha outside. It's a constant. So that simplifies things again. Oh, and the next thing we need to do is we need to replace the dx. Remember, dx is equal to the xi over alpha to the half. So in fact, what we're going to do is replace the dx in here with the dxi, and that means we need an alpha to the half. So what can we do there? We've got to bring that alpha to the half outside of the integral, so that'll end up being, of course, alpha to the 3 over 2 in here. So I was able to actually erase a few points, and but it's still pretty complicated. So what's my point? It turns out that there is a very important relation of Hermite polynomials, and that relation is as shown. I'm going to put it on this slide in here, and you can take this to the bank. Try going to all the Hermite polynomials and plug them in and demonstrating that this is in fact correct. Okay, so hv plus 1 minus 2 times, and this xi times hv of xi plus 2v hv minus 1 of xi, that equals 0. And this is the cool trick, and this is where we're going to use this to help us with selection rules. It's our cool trick. This is called a recursion formula. And so how are we going to use it in this particular case up here? Well, what we're going to do is we're going to rearrange this equation a little bit. Okay, so here's our recursion formula from the previous slide. I've just rearranged it a little bit in here, and I've rearranged it to have this xi function multiplied by the Hermite polynomial h sub v on the left hand side. And what that allows me to do now is actually plug this in to this expression down below, right? So I'm going to replace one of the xi terms. Let's write this out. So I'm going to get my e to the minus xi squared, and then I'm going to have my xi in here. It's an odd function in and of itself, and then I'm going to replace it by these brackets in here. I'm going to plug in v, h v minus 1, function of xi plus 1/2. So what I've done basically here is I've divided by 2 across the board as well. So that's half hv plus 1 of xi. So there's what I've plugged in. Maybe I should use these, maybe I'll put in square brackets in here. Show you what I've done. Multiplied by hv, still a function of xi d xi. But the key piece here is now when I expand this particular bracket, right? So I've got, this when I expand this bracket, I'm going to end up with an hv minus 1 term multiplied by an hv term, again multiplied by the rest of that psi function, right? And I'm also going to get a half hv plus 1 term multiplied by an hv term. So it turns out that by using this recursion formula, what this tells me, remember, I have these orthogonal Hermite polynomials, right? The thing that distinguishes two solutions to the simple harmonic oscillator Schrodinger equation, the thing that distinguishes those solutions is that Hermite polynomial. So these Hermite polynomials, when I multiply them by each other, I'm going to get an even value multiplied by an odd value, which gives me an odd function. Then when I take the integral of that with respect to d xi, I'm going to get a 0. So in other words, what happens is I end up, this seems really tedious, but these pieces in here, when I expand these brackets, I end up getting these orthogonal values. And what happens is my integral simplifies, right? So these terms disappear, and because of orthogonality, these terms go to 0. So the key here is that this recursion formula makes integration less tedious and effectively qualitative. Okay, and the last point that I wanted to get to was basically saying, so in this final section we're going to talk about how recursion formulas actually help explain something I introduced quite arbitrarily a few slides ago, and that is selection rules. So before we go into this, I'm going to plant a new seed and introduce the idea that the probability of a transition from a ground state or a state V to a state V prime is proportional to the square of the following integral. So it turns out that when light interacts with matter, we have to have that light interact with an oscillating dipole moment in the molecule, right? So light is an oscillating electromagnetic field, and an oscillating dipole moment would resonate with that light, and that's what we would call the transition dipole moment. So we have to couple the ground state in here with the excited state through a dipole moment in the molecule. So that's where we're heading in advanced quantum mechanics and into spectroscopy. But we're going to think about this now using this simple idea of the recursion formula. So I've written out the integral in here, and the important thing to recognize is that this mu z function is the z component of the dipole moment. We're also going to recognize that we can use our Taylor expansion approach, so we can have mu z, so function of x, is equal to mu naught plus d mu by dx, where x is equal to 0, multiplied by x, plus, and so on and so forth. That's our Taylor series expansion. So again, mu naught is the dipole moment at the equilibrium bond length. But of course, here's maybe we have a hydrogen and a chlorine, so a hydrogen chloride molecule. So as that molecule stretches backwards and forwards, the dipole moment increases, because dipole moment is equal to charge times distance. We might also get some compression where these two atoms get even closer together. So what we're seeing in here is in fact a changing of the dipole moment as we change that bond length. So that's represented by this d mu by dx term, and it's that changing dipole moment with respect to time which is going to interact with the oscillating electromagnetic field in the light source. But most importantly, when we take this series, what are we going to do with this series, and we plug this series into the integral, what do we end up with? So let's do that. So of course, the mu naught is a constant that comes outside of the integral. And inside the integral, because of that constant gets pulled outside, this first term in here, you're going to say, well, you're going to realize straight away it's actually going to cancel out because of orthogonality. So then we're going to have, as we continue with the expansion of our series in here, we've got the d mu by dx, x equals 0 in here. Here's our integral from infinity to minus infinity. And now we've got that x term that's left over in the series, okay, v prime. So that's why this second term does not go to 0 because of orthogonality. So the key here is that this first term is going to cancel. That cancels because of orthogonality. And this second expression here, we're going to use our recursion formula to help us. And if we go back one slide, here is our recursion formula that we're going to use in here. We're going to use that. So what are we left with? So let's think about this for a second. In our recursion formula, we had a xi times hv of xi equals v times hv minus 1 of xi plus 1/2 hv plus 1 as the quantum number xi. So now let's start to expand this, but what we're going to recognize in here is we've got this wave function multiplied by x. Okay, so we're going to replace this wave function multiplied by x. We're going to replace that with xi over alpha to the half n v h sub v e to the minus alpha x squared over 2. Okay, so we plug that in, and that's where this h term is going to come. We're actually going to get a xi h v term, and that's familiar to us from here, right? So we've got this xi and we've got this h v term. That's where this piece comes in. So this leaves us with, when we plug when we expand this all so that we have our normalization constants, by the way. Because remember, we've got two quantum numbers in here. And then we've got the d mu by d xi. We're going to replace the x with the xi across the board. We've done this in previous slides, so I'm going to jump through it fairly quickly. And then I'm going to replace this, right? So I'm substituting now this expression and combining this expression, so that what I'm going to end up with in some square brackets here is a v hv minus 1 of xi plus 1/2 h v plus 1 of xi. Outside the brackets, I've still got my h v prime e to the minus xi squared dx. So nothing particularly new here. I've jumped a few steps. But the final point here is, the final question I'm going to say is, so what are the only values of v prime for which the integral does not vanish to 0? And really what I'm saying here there is, what are the only values of v prime for which I actually get a non-zero transition dipole moment? That means I'm going to actually get a transition. I'm actually going to get a spectroscopic signal that I can measure. So what are the only values of v prime for which the integral does not vanish? And here I'm using the principles of orthogonality again. So if we think about this, right, if I expand this bracket, let's consider the hv minus 1 term and the hv term. So the only time when this integral is not going to vanish is when v minus 1 is equal to v prime. But remember, I'm starting from v in my transition. I set this up in my transition dipole moment to go from v to v prime. So it turns out that in this integral, v minus 1 must be equal to v prime. In other words, in that particular case, h v minus 1, h v prime is not equal to 0 if v minus 1 is equal to v prime. Okay. That's this first part of the integral. The second part of the integral, I've got an h v plus 1 of xi. Okay, so when that multiplies by h v prime, okay, orthogonality would say if v plus 1 and v prime were different, then that would be equal to 0. So the only values of v and v prime for which the integral does not vanish is when v in here, so in other words, v plus 1 must be equal to v prime. What does that tell me? It tells me that delta v must be equal to plus or minus 1. And therefore the selection rules they fall out of the mathematics and orthogonality. So they fall out of the mathematics and the principles of orthogonality. Okay. And also, I've introduced the idea here that oscillating electromagnetic radiation must interact with an oscillating dipole moment in here. That's what this expression was here in order for spectroscopy to take place. So a couple of very important factors I've introduced in this case. And if you think about it, and this is, again, this is in I think section 5.112 or 5.12 of your textbook goes into a little bit more detail, but it's by using this recursion formula, the properties of those Hermite polynomials that allow us to simplify the integrals and allow us to kind of demonstrate using orthogonality what the values of v and v prime must be in order to get a spectroscopic, an observable spectroscopic transition. Okay, a lot to take in there. We've finished up chapter 5. That was the harmonic oscillator. A lot of ideas have been introduced here along the way. Next up, we're going to be thinking about the rigid rotor. So we're going to go slightly deeper to a more complex system as we work towards the hydrogen atom. So thank you very much for your attention.